Hello. So, this is going to be the last video, the last thing that you're going to learn all year long. I know, super excited. So, it's going to be called Permutations and Combinations. And we're going to start off with the counting principle. And actually, it's something that we talked about previously when we were doing the counting principle of how many possible outcomes of one event and then another event are happening or another event are happening, and it's kind of compounded on top of each other. If you remember, I was talking about at the beginning of the year during questions of the day where we have like our hands and trying to find all the different combinations of something happening. That is the counting principle where you have to multiply all of those different combinations or all of those different outcomes together. So that's where we're at. So the counting principle is just the basic counting principle or the fundamental principle of counting says that if you have A possible outcomes for one event and B possible outcomes for another event, you can get the total number of events by just multiplying the two events together. So we take A times B. Now, you could also list out all the possible outcomes, which we have done in the past. So if I have an example here, I have a couple plans on having 4 children. How many different girl-boy outcomes are there? So when we're taking a look at the different girl-boy outcomes, we can list all of them. So the first way is to list all the events. We can still do that. So we can list all outcomes. So if I list all the outcomes, right, so let's just start with girls. So we have all 4 are girls. So we have girl. We can have 3 girls, and then we can have a boy. We can have 2 girls, a boy, and then a girl. We can have a girl, we can have a boy, and 2 girls, or we can have a boy first, and then we can have 3 girls after. We can also have 4 boys, and then we can have 3 boys, and then a girl, much like my sister-in-law. She had all 3 boys, and then she had a girl finally. She tried for a girl. And then you got 2 boys, a girl, and then a boy again. You got a boy, a girl, and 2 boys. And then, or you have a girl first, and then you got 3 boys after. Let's say you have 2 girls and then 2 boys. Let's see, you can have a girl, boy. You can have a girl, 2 boys in the middle, and then another girl. So these are all the combinations. You have 2 girls. Let's see here. And then we got 2 boys back to back, 2 girls back to back. You could have a boy, a girl, a boy. And then you can also have a boy. We don't have boy, girl. Yeah, right? Boy, girl. Yes. So there are a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 16 different outcomes. Awesome. 16 outcomes for having a different boy-girl outcomes. That's a lot. So the second way is that if we have a large amount of different things that we have to do, it's going to be much easier to use the counting principle, which sometimes I even forget some of those combinations. So in my head, especially when I'm trying to make sure that I'm not double counting those combinations, so it'd be quite difficult. So this is kind of how I like to set up our counting principle. So if I know I'm going to have 4 different children, so I have 4 different people. So 1, 2, 3, 4. This is going to be my first kid. This is my second, third, and then my fourth. For my first kid, there are 2 different outcomes. Either it's a boy or it's a girl. 2 outcomes. So then we have another opportunity of have 2 different outcomes. For the second child, we can have a girl or a boy. For the third child, we can either have a girl or a boy. So we have 2 outcomes here. And then here we have, for the fourth child, still 2 outcomes, girl or boy, either or. All we're going to do is multiply all of those together, because think about back to our multiplication rule. We want a girl and a girl and a girl and a girl, or a boy and a boy and a boy and a boy. We have all these and possibilities. So we would just multiply all those together. 2 times 2 times 2 times 2 would give you 16 outcomes. Much easier, especially when you have a lot of different things. So for example, we could list out all the outcomes. So this was our second way, is the counting principle. Forgot to write that down. All right, so first way, we could list out all the ways that we choose always, all the way we choose sometimes, and never. On a quiz in calculus, there are 8 questions on the quiz. How many different ways can we answer the questions if you completely guessed? Okay, so those that took the ACT, you just completely guessed all of it, all those juniors. Maybe we'd have some opportunities here to figure out how many different ways we could have completely guessed on the ACT, but that would take a long time. So, for example, if I wanted to list out all my outcomes like I did here, we could do that. That would be great. But we have 8 different questions, so we have to do that 8 different times. So I could do always, that's 1, 2, 3, 4, 5, 6, 7. Could have guessed it 7 times. And then we could have guessed always, so the first, 8 times. 1, 2, 3, 4, 5, 6, 7. There's 8 questions, not 7. Or for the first 7 questions, I could have guessed always, and the last one I could have guessed sometimes. Or for the first 7 questions, I could have guessed always, 1, 2, 3, 4, 5, 6, and then guessed a never. This is going to take us forever to figure out all the different outcomes and all the different possibilities. So, using that multiplication or the counting principle, the fundamental principle of counting, either one, would be a lot easier, because I have 8 questions. So I have the first question, second, third, fourth, fifth, sixth, seventh, eighth question. For my first question, so I have question 1, 2, 3, 4, 5, 6, 7, 8. For my first question, I have 3 outcomes that I could choose. I could choose always, sometimes, or never. So I have 3 outcomes here. For the second question, I once again have 3 outcomes here. I have 3 outcomes here, 3 outcomes here, 3 outcomes here, 3 outcomes here, 3 outcomes, and 3 more. Whew. So in my calculator, I can type in 3 times 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 3. Or I can just say, hey, I have 3 options, multiplying 8 times together, and we get 6,561 outcomes. It would take forever to list all of those 6,561 outcomes. So I would suggest you to use that multiplication or the counting principle. I keep saying multiplication, but the counting principle for your values here. All right, last one. It says there are 31 different sandwich options at McDonald's, not including breakfast. So just like lunch and dinner. We have 3 different size options for fries and 3 different size options for drinks. How many different meals can be ordered from these 3 options from McDonald's? Okay, so once again, we have all these different things. The first thing that we can choose from is our sandwich size, what type of sandwich. The second thing that we choose is our fries. And the third thing we can choose is our drink. So these are our 3 events that are happening. So we're going to take the total number of outcomes and we're going to multiply them together. So the number of sandwiches, we have 31 possible sandwiches that we could choose from. But we also want a fry and a drink. So this is when we're multiplying them together. So we have 31 sandwiches. And we have, for our fries, 3 options here. And we also have 3 options for our drinks. So I take 31 times 3 times 3. I get 279 menu options. and that is the counting principle. Now, we can actually utilize the counting principle when we're taking a look at permutations and combinations, which is what we're going to do next. So, the next type of counting technique that we're going to use is when a certain number of objects from a fixed number of objects, and order matters. So, looking at order matters. So, the order would matter of what we would be taking a look at. Whenever you're trying to decipher between permutations or combinations, this is the big difference. Permutations is where order matters. Combination, order doesn't matter. So, for example, if you have 30 people in your PE class and they're all running a mile, right? You're real competitive. PE teacher says, hey, I'm going to offer a prize to the first, second, and third place finishers only. And we're going to see how many different top 3 are there. Okay? We can still use the counting principle, right? I know that I have 3 different places. I have first, second, and third. So first, second, and third place. Still have first, second, and third place available, and I'm still going to be multiplying these together because I want first and second and third. Now, recognize that the order does matter here. So first place is different than second place, it's different than third place. You're all going to get different prizes, let's say, for first, second, and third place. He's not just saying, hey, the first 3 people to cross the line are going to get the same prize. No, first place gets something different, second place gets something different, third place gets something different. So, using the counting principle to find these, right? For the first place, no one's crossed the line yet, so you still have 30 people in the class that could cross that line first. So there's still 30 different people that could cross. But once one person crosses that line, there's only 29 people left in the running. In the running, because we're running a mile. Anyway, once that second person crosses the line, then we're only going to have 28 people left for the third place. So the counting principle says that we take 30 times 29 times 28, and we get 24,360 outcomes. A lot of outcomes. Now, this pattern where we have 30 times 29 times 28, we take each number and we multiply it by the number that was number before it. Does that make sense? So we call this a factorial. So factorial is read as like a little exclamation point, and it's just read as factorial. So for example, I have 5 factorial. I take 5 and we multiply by every number after it. If that makes sense. So we take 5 times 4 times 3 times 2 times 1. I think you said preceded, but it's after. So we have 5 times 4 times 3 times 2 times 1. That would be our factorial. So 5 factorial is read 5 factorial. However, just be careful because 0 factorial is actually 1, and 1 factorial is also 1, so just be careful on that. So 30 factorial would be, we take 30 times 29 times 28 times 27 times 26. And we can figure out how many different ways that we can place in all the different ways. How many different ways we can place in first through 30th place. And really we're just like multiplying all the way down until we get to 3 times 2 times 1. Now, you can actually use your calculator to calculate this as well. So when you're looking at 30 factorial, you are going to go to this math button here on the left, and you're going to go to PRB, and you're going to see this little factorial guy. The only thing is you got to get it right in 30 first, and you hit math, and then you scroll over to PRB, scroll down, or click 4, either one, and it actually calculates 30 factorial for you, and that is going to give you Remember, this E stands for times 10 to the 32nd power, so we'd move this decimal place over to the right 32 times. That's going to come in handy later on when you start calculating some things too. All right, so taking a look at if this wasn't what our original problem showed, so looking at the 30 factorial, right, that's not something that we looked at here. That's not something that our original problem that we were trying to find, the top 3, came from. So where did the rest of this 27 all the way through 1 go? Well, what we have to do is divide out from 27 all the way through 1. So really what we did is that we took our 30 factorial, right? So our 30 times 29 times 28 times 27 times all the way down to 3 times 2 times 1. And we had to take out, because we only wanted the first 3 places, we wanted to take out everything from 27 all the way down. So we had to divide by 27 times 26 times all the way down to times 3 times 2 times 1. And really what we did is that we just kind of canceled out those values, and we got 30 times 29 times 28, our first 3 places, because we had to take out the top 3. Really, I took 30 factorial, because that's what our 30 factorial would be, divided by my 27. Well, 27 times all the numbers that were before it is actually 27 factorial. So where in the world did the 27 come from? Remember, we just took the first 3 places. So we had to take the 30 students, and we just wanted the top 3 of them. So the first 3 places in them. So really, we took 30 minus our 3 to get 27. And that's how we got our bottom number there. So this is the number of places that we want. This is the amount of people that we have to choose from, and we call that n. So the number of ways we want to arrange n amount of people, or n amount of objects. And this is how much we're choosing. We're choosing those first 3 options here. So when we're looking at an equation for it, I'm going to get to this piece down here later with the graphing calculator and everything. But just make sure that order matters when you're looking at the number of arrangements. You're going to have a lot of different arrangements because your order matters, meaning that repeats are going to be allowed inside here. Meaning that you can get first place in many different ways. Just keep that in mind. So if I had my number of ways to arrange the order n distinct objects taken R at any time is, we have our permutation because order matters, and we have n choose R. That's how I kind of say it. So n is the number of options, or the number of objects that we have. And this is the number of positions that I like to say, number of positions. So when we're looking at our n and our r, we took our n factorial, right, our 30 factorial, because we had 30 people. So number of objects, number of people that we're talking about, divided by the number of positions that we wanted. So in order to get the number of positions that we wanted, right, the first 3, we had to take n minus our r. R is the number of positions. So we take n minus r, and that's how we got our 27. We divided that out. I don't like using formulas, not something that I like. I like using the counting principle. I keep calling it the multiplication counting principle. It's just counting principle. So the counting principle is what I like to use because it just makes sense. You got 3 positions. How many options do you have for each position? And you go from there. Order matters, so you just got to make sure that you're looking at figuring out how to get from 30 to 29 to 28. So yes, the formula is not really that important here, but it will become important when we look at combinations here in a minute. Just make sure that repeats here are not allowed. So making sure that we're seeing if repeats are allowed, we're looking at the counting principle. Okay. So we have 30 options, 30 options, 30 options. Once one person is finished, they can't place again. So, taking a look at some examples. Okay. So, looking at our example here, we have a 4-digit pin using 10 digits. And it says repeats are not allowed. So they are not allowed. If repeats aren't allowed, so we have a 4-digit pin. So once again, we have first pin, second pin, third pin, fourth pin. And we're going to multiply these together. So we have first number, second number in the pin, third number in the pin, fourth number in the pin. So looking at my first number in my pin, I would have 10 different digits for my first number. But repeats aren't allowed. So for my second, once I use 1 for my first digit, I can't use 1 again. So I'll have 9, and then we have 8, and then we have 7 options for our third and our fourth pin. And we multiply those together, and we get 5,040 outcomes. Versus if we create a 4-digit pin using 10 digits and repeats are allowed, how many different pins can we create? I can create 1, 1, 1, 1. I can create 2, 2, 2, 2. I can create 3, 3, 3, 3, or 4, 4, 4, 4. So if I have 4 different values or 4 different pin numbers, 1, 2, 3, 4, I would have 10 digits here times 10 digits allowed here times 10 times 10 because I can repeat them. This is the counting principle. Permutations, counting principle. 10 times 10 times 10 times 10, or I take 10 to the 4th, and I have 10,000 opportunities. Less here, no repeats, repeats. All right, librarian has a pile of 20 books and needs to choose 5 to place in a specific order on a shelf. So because it's a specific order, we can't repeat anything. So how many options does she have? So specific order means that we have different options and with no repeats. So we have first place, second place, third place, fourth place, fifth place. So really, I'm going to take 20 books for my first place, second book, third book, fourth book, fifth book. I have 20 books. Once I choose the first one, obviously it can't go in the second place. So we have 19 times 18, 17 times 16. We multiply those together and we get 1,860,480. 1,860,480 options. All right. You can also create a password. So we're looking at another example. You need to create a password using lowercase letters and digits. If repeats are not allowed, how many different options do you have for an 8-digit password? So once again, repeats are not allowed. So if I want 8 digits, 8-digit passwords of letters and digits, so lowercase letters. So let's see here, we got 26 letters in the alphabet, and I'm going to draw my lines. 1, 2, 3, 4, 5, 6, 7, 8 digits. So let's see here, we have, 26 letters, and then digits, we have 0 through 9, so we have 10 digits. So we have technically 36 different options for my first letter, or for my first digit password, because I can have a number or I can have a letter. So looking at not allowed, we would have 36 for the first one, times 35 for the second, 34, 33, 32, 31, 30 options, and then 29 options. Oh, there's going to be a lot of options. Let's see, there's 1, 2, 2. Typing this in my calculator here. I'm just reading off the calculator screen. 6 options. Tons of options. Tons of options. All right, so what if order didn't matter? So what if order didn't matter? Then we would have kind of a different counting pattern where one, we have our permutations of the same kind of single occurrence, but then we kind of have to eliminate our repeats that we have. So let's go back to our race. And let's say our PE teacher will award the prizes to the top 3 finishers, and the order doesn't matter. They're just going to give all the first 3 players a prize. So since the first 3 players that cross that finish line, they can finish in any order. So the order doesn't matter which they finish. They're going to get the same prize regardless. Maybe they get extra credit, and maybe they get whatever. But all 3 are going to get that extra credit, no matter what. They're not going to have different point values or anything else. So let's say Anson, Bree, and Caden are all running in the race, right? So let's figure out how many different ways can Anson, Caden, and Bree all finish the race in the top 3. So, because then we have to kind of eliminate those out of our original value and go from there. Because the order of which they do things doesn't matter at all. So let's say Anson finished first, then it was Bree, and then it was Caden. Maybe then we have Anson finish first again, Caden finish second, and Bree finish third. And maybe we have Bree finish first, and then we have Anson, and then we have Caden finish last. Maybe then we have, third, not last technically. Let's say we have Bree, and then we have Caden, and then Anson finishes third. I keep saying last, but you know what I mean. So let's say Caden finishes first, and then we have Anson finishes second, and Bree finishes third. And then let's say that Caden still finishes first. We have Bree finishing second, and then we just switch those 2, and Anson finishes third. No matter how they go through and finish in the top 3, there are 6 different ways, right, that they could finish. Now, I could have listed all those, but I could have also used the multiplication or the counting principle. Keep calling it the multiplication rule. But I could have said, okay, there's 6 ways, or I know that there's 3 positions. There are 3 people that we're looking at. 3 times 2 times 1 would give me my 6 outcomes, right? Either way. So that's where our 6 is going to come from. 6 ways that any 3 of them could win their extra credit. Now, if we want to make sure and figure out how many different ways that those individuals could win, right, we would need to make sure that we eliminated these repeats out of our permutation. So remember, our permutation was the fact that we could do 30 times 29 times 28, right? But we wanted to make sure that we eliminated those 3 times 2 times 1. So really what we're doing here is taking our 30 factorial. Remember how we did our permutation? We did our 30 factorial. To get rid of that 27, we took 27 factorial. But we're also now adding in our 3 factorial to get rid of those and eliminate those different pieces there. So this came from our permutation, and now we're eliminating, because order doesn't matter, eliminating those 3 factorial out. And when I do so, even when I just multiply this, these are exactly the same. Multiply these, divide by how many different, the order of which we want those, and those 3 times 2 times 1, those first 3 individuals, they can be coming in and getting that extra credit in 6 different ways. Now we only have 4,060 outcomes. So notice here that our combinations are a lot smaller because the order doesn't matter here. because it's not a very specific order that we're looking for. Those top 3, they can finish, they can get their extra credit. There are 6 different ways to do that. We had to eliminate those extra repeats that were in there. So when you're looking at your formula for your combination, it's going to look really similar to what we did for our permutation, with one added feature of eliminating those repeats and making sure that order doesn't matter. What I like to do when I go through these is really just look at our permutation and then take a look at how many different ways that we can then eliminate those repeats by taking what we're choosing and taking the factorial of what we're choosing on the bottom. Because really this is just 3 factorial. It's 3 times 2 times 1. So looking at the formula, we have the number of ways to arrange in order in distinct objects taken R at a time is. So now because we're looking at in a specific order where order doesn't matter, we have our combination of n choose R. And remember, this is the number of ways, which is n. Just like how we said we have the number of objects, same thing. And we're looking at in an R specific amount of positions. So take an R or choosing a certain amount. Our formula is n factorial over, and we have n minus R factorial times our R factorial. So we have the number of ways or the number of objects that we have. So number of ways, we want actually the number of objects here is n, number of objects. And R ways, so how many are we rearranging them by? Or what is the number of positions that we have? So we take n minus R factorial, which is basically the permutation, and we're just dividing out the repeats. That's really all we're doing here. So let's go ahead and try some examples. All right, so once again, I kind of like to take the permutation, divide by how many ways that we're trying to rearrange it, and remove the repeats. Because our order doesn't matter here, because we're looking at we have how many different jurors of 12 can be selected from a pool of 30 people. So this is our number that we're trying to, so the number of positions that we're looking at. So this is our R value. And then 30 people is the number of objects, so our N objects. So how many different juries of 12 can be selected? Once again, once they're in that group of 12, it doesn't matter how I picked those 12 people, they're going to be on the jury out of the 30. So if I want to figure out how many permutations there are, that's really what I'm doing. I'm taking the number of permutations and dividing out my repeats, or our R factorial. That's all we're doing. So if I take my number of permutations, so I have 12 different values here. So I have 12 options. So I have 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12 options, right? And I have 30 people for the first one. Then I have 29, then 28, then 27, then 26, then 25, then 24, then 23, then 22, then 21, then 20, then 19 people for my last, because once they're chosen, they can't be chosen again. I'm going to divide out my repeats, because my order of which I'm looking at when we select those 12 people, just like Anson, Bree, and Kaden all going through and crossing that line, doesn't matter how they crossed the line and they got in the first 3 positions, they still get that extra credit no matter what. So we divided by 3 times 2 times 1, which is the factorial of the number of positions that we're looking at. So we divided by 12 factorial. And I can type all of that in my calculator. So 30 times 29 times 28 times 27, 26, 25, 24, 23, 22, 21 times 20, 20, 17. And divide by 12 factorial. and I'm going to get 8,493,225 total possibilities of choosing those 12 different jurors from the 30 people. Lots of different ways. All right, so we have at volleyball tryouts, there are 18 girls hoping to make the roster. If the coach only has 12 spots on the team, how many possible teams are there? So once again, 18 girls, that is the number of which we're looking at, and our 12 spots, which is our R value. So that's the number of positions that we're looking at on the team. So I'm going to take the total number of possible permutations. So I take my 18 times 17 times 16, 15, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 positions, and I divide it by my repeats. So my repeat is going to be 12 factorial. And I get 18,564 options. All right, you're on standby for a flight in Alaska. There are 12 people waiting, but only 3 seats available. How many different combinations of people are there? So when you're looking at how many different combinations of people are there, we have, once again, 12 people total, 3 seat options. So we have 12 times 11 times 10. That's how many permutations we would have, and we need to delete out or remove those repeats, which was our 3 factorial, because we had those 3 positions. So we remove that factorial, and I get 220. All right, so I'm going to show you the calculator version of all of this. So when we're taking a look at our calculator, we'll take a look at this one right here. So I take a look at we go to math. Now, before you go to math, this is where you're going to find it. You're going to go to PRB again, and you can find permutation and combination. So you can find both of those. So if I wanted to find the permutation, so where order matters, that's what you're going to choose. Combination right here. You just have to make sure you know what your N and your R are. So here, we know my N was 30 people. So I type in 30 first, hit the math button, go over to PRB. We have our combination because the order matters, order doesn't matter here. Once you choose the 12 people, doesn't matter. So we're going to click combination, and we want an R different positions, and we get our value. Now, when you're doing this, you cannot just type this into your calculator. You must show your work. So when I wanted you to show your work, this is what I mean. I say, hey, we have our combination, and we want 30 people, and we're choosing 12. 30 people choosing 12. This is also on your phone calculator. If you turn it sideways, you'll see it. I want to see the formula then. Okay, I want you to show me the formula. So we have our 30 factorial, which was our total number of ways that we can go through and choose those people. And then we have 30 minus 12 factorial, and then we have 12 factorial. And you get your answer of the same thing. I need you to show me your work regardless. Show me your work regardless. So here I could choose, again, I have my combination. I have 12 people. I want to choose the first 3 positions where order does not matter. So once again, I could do 12, math, go over to PRB, go down to your combination, and we get 3. It's great that you know your answer, but I need to make sure that you know how to get there. So we take our 12 different options. We take 12 minus 3. So that's our number of permutations. We delete out our repeats, which was our 3 factorial, and we get 220. Either one of those work, I would be okay with. Same thing up here. We have our combination because our order doesn't matter. And we have 18 girls, and we're choosing 12 spots. So I would have 18 factorial over our 18 minus 12 factorial times our 12 factorial. So I take 18, math, go over to PRB, combination. We want to choose 12, and we get our 18,564. Same thing we were doing before. All right, looking at our last question. At a Dip by the Bay, the local ice cream shop, you want to choose a cone to eat. There are 4 different types of cones. You can only choose one. And 20 different types of ice cream, 5 different types of toppings. How many different combinations can you choose and create? So we have 3 different things that we're looking at. We're looking at cone, plus we want the number of different ways we can do ice cream, plus the number of toppings. So looking at the number of ways that we can choose a cone, so out of the cones, we have, I'm going to use our notation here. So we have our combination. We have 4 different cones, and we can only choose one. We have 20 different toppings, and we can only choose 3. So we have combination. We have 20 different toppings. It doesn't matter how I put the toppings on. This is why this is a combination. Doesn't matter how I put the toppings on. We still got it. So we have our 20 different options, and we're going to choose only 3 of those options. We also have a combination again because it doesn't matter how I choose those toppings. We're going to make sure that we have 5 different toppings, only choose 2, so we have 5 total. We're choosing only 2. So we can look at the calculator to calculate all of these if we really wanted to. We have 4, and we want choose 1. Well, we have 4 options to choose that first one, and we would have our 4 options here, plus our 20 different ice cream flavors, and we're choosing 3, which was 1140. And then we also have 5, and we're choosing 2. So we have 10 options. We add those together, so we take 4 plus 10, and we get 1,154 options. So permutations are really just your counting principle, just a little bit shorter, right? Where we're only going to be having a specific amount. For combinations, we have to make sure we take our permutation and divide out our repeats. I don't necessarily like the formula. I understand it better when we kind of write it out, but it's totally up to you, whatever you choose. But if you choose to use the calculator and use this, you've got to show me the formula. You've got to show me some work. You cannot just type it into the calculator. Alrighty, so on your worksheet here that you're going to be getting, you're going to be determining whether it's a permutation or combination, and then answer the question using the formulas or the counting principle. Either way, you got to show your work. Okay, you have to show your work. So tell me if it's permutation, combination, and go from there. You have 6 different questions that you have to do. All right, and we'll be doing more practice over this as well.